Hi folks, thanks for watching. This is Mr. Ackerman here, and this video deals with a worksheet that was emailed out to you at the beginning of the semester here. It's in the Unit 1 course pack, and the topic is Grade 12 Diagnostic Review of Grade 11 Motion Unit. And what that means is it's just an opportunity for you to do a self-diagnosis of how much you remember from the Grade 11 unit on kinematics. This is going to talk about kinematic equations and velocity and position graphs and things like that. It's not going to be marked, so no stress. However, it should give you some important feedback maybe on how much work you're going to need to do, at least in the beginning of the unit, in order to get your brain into physics mode. Anyway, there's 4 questions, and what I'm going to do is give you some hints on each one, and you're also going to get to see some of the problem-solving techniques that I like to use. So if you're stumped on this, this is a good place to start. If you're still stumped after watching this, you've got your classmates who might be able to help you, as well as myself. And another option would be to look in the solution binder that I keep in the classroom. There are full solutions to this problem set, so that if you want to check what you're doing or see where you might be going wrong, that's another alternative. All right, let's not waste too much time talking about that. Let's get started. The first question deals with actually, I don't even have the first question in here, and that's because I deleted it by accident. So how are we going to get around this? Easy. We're going to add in that first question. Just give me 2 seconds here. There it is. Okay, so right about there, I believe that's it. There we go. There's the question. So let's just put that in here. Perfect. Okay. It talks about a physics teacher who is running around outside, and he does a number of things. He moves in a bunch of different directions, taking a certain amount of time. So starting from his house, he runs north, takes a certain amount of time. He stops for a certain amount of time. Then he runs in a different direction, a different distance, taking a different amount of time. And finally, he makes a turn and moves in yet another direction, a certain distance, in a certain amount of time. And then they ask you to calculate a whole bunch of things like average speed, displacement, average velocity, position, etc. And so how do you go about solving this problem? Well, whenever I solve a problem, there's always 2 things that I do. The first thing is I draw a diagram. So you don't really have much of a chance on a lot of these problems if you don't draw a diagram. It is absolutely essential to draw a diagram. I can't stress this enough. A lot of students don't draw diagrams. They feel it's not worth it or it takes too much time. And in my mind, what they're basically saying is, I'm going to accept a lower chance of success in order to save a few seconds of time. Clearly a very poor trade-off. So if you're someone who doesn't like to draw diagrams, you should probably get into the habit of it. I can assure you, after teaching this course for many, many years, that the people who draw diagrams simply do better. So I ask you for your own sake to please do that. You're going to be more successful. And the second thing that I always do when I'm solving a physics problem is I write the formula of the thing that they're asking for. A lot of the things in physics, for example, average speed, have a definition, and I like to write that down. For example, if you remember from grade 11, the average speed, the symbol is v_av. There's no vector hat because it's not velocity, it's speed, it's a scalar. So v_av equals delta d over delta t. And of course, you got to know what all these symbols mean. This delta d, no vector hat, means total distance. And this thing down here, of course, means the total time. So now that I've written down what it is they're asking me for, I know what to go find. And if I have a good diagram, I have a good chance of finding that. Over here, they ask for displacement. Now, what is displacement? Displacement is the symbol delta d with a vector hat, and it, of course, refers to a delta, a change, in d vector, the position. So I can write that down if that's something I know. The funny thing about displacement is it doesn't care what path you took. All it talks about is a change. So where did you start and where did you finish? Give me a straight line between those 2 points. of course, it's a vector, so also don't forget that you need to include magnitude, and you also need to include direction. So those are the first two things they ask for, and right away, hopefully things are starting to get clearer and physics problem solving is getting a little bit easier. If I draw myself a good diagram and I know what it is I'm looking for, I have a really good shot at solving a problem. Let's take a look. How would I solve this? I'll get you started. Let's use let's use a different color that's maybe a little bit easier to see. There's red, and we'll use some straight lines here. It says that he starts at his house and he runs north. Then he stops. Then he goes a little bit south, a little bit east. Right away I see him dealing with directions. So let's make this easy if we can. Let's denote those directions. The first thing I'm going to do is make it so my diagram is going to be meaningful and helpful. It says he starts at his house. He goes north. Okay, well, north is up like this. And it says that that's 5 kilometers. So let's say 5 kilometers there. Okay, now what happens? It says he stops. So let's write that in. Then it says that he goes south 42 degrees east. Okay, it's a straight line again. Now, that means from south, turn 42 degrees to the east. Now, it's close to a 45-degree angle, so I'm not going to do this. I'm not going to do that. I'm going to try to make my diagram as accurate as possible without taking the extra time needed for a scale diagram. 6.5 kilometers is what they ask for. This is 5 kilometers, so now it's a little bit longer, and it's on like a 42-ish degree angle. I don't know, maybe it looks something like that. This is not a scale diagram. I'm just doing my best. 6.5 kilometers, and the angle south 42 degrees east, that means that in here is 42 degrees. Okay? Next up, it says he runs south for 4 kilometers, so we're going to need another straight line. It's going to be down like this, a little bit shorter than this line would have been. So this I'm trying to show is 4 kilometers, and voila, we see that there was a start over here, there is a finish over here, and now what are they asking for? Well, for example, just getting back to the last thing we discussed, displacement. Remember, displacement's a straight line from start to finish. Well, hey, because I have a diagram, the answer is pretty obvious, at least, oops, I'm going to use a straight line feature. It's pretty obvious, at least to see. Doesn't mean you're going to have an easy time solving for it, but at least you'll know what it is you're going for. This is the total displacement, delta D with a vector hat. Now, it looks like a parallelogram. Is it parallel? Well, no. One of the sides here is 5 kilometers long, and the opposite side is 4. So right away, it can't be a parallelogram. So get that idea out of your head immediately. However, is there some way that we can solve this? Well, this is where I'm going to leave it to you guys in your groups to work on this. But can you think of some way of solving this weird shaped figure? I'll give you one hint, which is that if you use, if you want to think about using trig ideas, for example, sine and cosine laws, you'll be able to do this. Now you might be thinking sine and cosine law only deals with triangles, and there's no triangles here. You'd be right. However, we can break this diagram into some triangles, and I'll show you how. Take the first displacement, the 5 kilometers, and the second displacement, 6.5 kilometers, and deal with them alone. Just deal with this triangle first. In other words, based on the 5, the 42, and the 6.5, see what this green line comes out to. What that's going to do is it's going to suddenly make it look like you're only dealing with that. And then you're going to see, oh, hey, there's one triangle. I can solve this again. In other words, here's your hint. Do sine and cosine law twice on this question, and you ought to be able to find the displacement there. Average speed is total distance over time. I think from your diagram you can see what the total distance is. I think you can also figure out the total time if you just read the question carefully. Average velocity, well, at this point I'm going to leave it to you. What is the definition of average velocity? I bet you if you look that up, you might be able to figure out what that is. And then in the end, part D, the final position. But remember, position is a vector that has what's called a reference point associated with it. You can't talk about the position of something without mentioning a reference point. Like you can't say something is 5 meters away. You've got to say 5 meters away from what? Well, 5 meters away from where I'm sitting right now. 5 meters away from where you're sitting? Maybe, maybe not. The reference point matters. Here the reference point is relative to where he solved the kinematic equation. So see if you can figure out the position relative to that point. Okay, folks, there's a bunch of hints on this question. Remember your resources for if you run into trouble. You've got your fellow classmates, you've got me, and you've also got the solution binder. And of course, maybe you should listen to this video one more time, the part on this question. Okay, moving along. Question number 2. Some lunatic physics student is making the following trip. Starts at school, runs south at a constant rate, reaches a giant physics equation sitting in the middle of the road. That's pretty scary. It's a certain distance away. Stops, screams for a certain amount of time, then staggers backward, accelerating at a certain rate until she gets up to a certain speed. Continues at this pace for 10 seconds, and then, well, some silly stuff that I wrote in there. Okay, what are you asked to do here? It says make a rough sketch. That means you don't have to include every single little detail. Make a rough sketch of a velocity time graph for the student's motion. It asks you to label the important numbers on each axis. So this doesn't have to be a totally accurate graph. It's just got to be a graph that has what I call the important numbers. What are the important numbers? The numbers where things change, for example, and some of these numbers up here, okay? We'll talk about it in a moment. Don't forget to label each axis. And here's a little hint. When you're dealing with a velocity graph, do you remember from grade 11, what does the slope represent? On a velocity graph, what is the slope? And also, what is the area? You learned this in grade 11. See if you can figure out what those mean. And if you forgot all this, then I do actually have a video that you can watch that deals with position, velocity, and acceleration graphs. It's for grade 12 students. It's a quick review. You can watch this, you can look it up on my YouTube channel, or if we're in class right now, I can tell you the exact name of it and you can look it up. It escapes me at the moment. However, this is an option for you on YouTube if you want a quick review of how to do these kinds of graphs. Okay? But anyway, let's talk about this for a minute. How do you convert a story into a graph? Well, again, do the things that you did here. You started with a diagram. You're going to have a harder time solving physics problems if you don't try to visualize them. So once again, we're going the diagram route. Now, what does a diagram look like here? First of all, this person is going in a one-dimensional motion. She's running south in the beginning. She stops. She goes backward, so that's north, and she continues moving north until the end of the question. So this is a north-south kind of thing. All right? So once again, we can draw our directions. Maybe I would do something like this. Since there's no east and west, I don't have to bother with that. This is north, so down is south. And let's see what happens. Starting from school. Well, I guess I better draw school. There you go. There's school. It's got a smokestack, I guess. Maybe it's the winter and they're heating the place. Okay. Run south at 3 meters per second constant rate until she gets 42 meters away. Can we draw that in here? Of course we can. We can show someone moving 42 meters. We can say that the person is moving at a rate of 3 meters per second. It says that she stops for 5 seconds. Okay, so we're going to write that in here. Stop. We're just collecting as much data as we can on our diagram. Then it says she staggers backward. She obviously starts from rest because she was stopped for 3 seconds, as we mentioned. Sorry, not 3 seconds, I apologize. It's 5 seconds. Okay, 5 seconds in there. She accelerates backward at a certain rate. You can write that in. Acceleration, 0.5 meters per second squared, until she gets up to 4 meters per second. Now at this point you got to think to yourself, okay, what is acceleration, velocity, what do these things mean? Well, you start from rest, you accelerate, so you're picking up speed. You pick up speed until you get up to a certain speed. How do you draw that? It's up to you how you want to draw it, but at least try to incorporate it into the diagram. Accelerate 0.5 meters per second squared until velocity is 4 meters per second. And of course, this is all going north, so we can write those in here. Every little bit that you try to include is going to slow you down just enough that you might be able to think of how to solve this. Remember, the goal is not to rush through these questions as quickly as possible. It's to think about them and become better problem solvers. All right. Continuing along, it says she does this till she gets to 4 meters per second, and then she continues at that pace for 10 more seconds. Now, let's stop and think critically for a moment here. If I told you that someone started from rest, picked up speed until reaching a certain speed, you'd know that she would move a certain distance. So we've got at least this distance in here. Now it says that at that pace, she continues for 10 seconds, and remember, she's at a pace of 4. So think about this. You're moving at 4 meters per second for an additional 10 seconds. What's that mean? 4 meters per second times 10 seconds is, of course, 40 meters. So we know for sure that ignoring the acceleration part, she goes an extra 40 meters. That's 4 meters per second at, 4 meters per second, not at, but rather 4 meters per second for 10 seconds. Now, look at your diagram. She originally went 42 meters south of the school, and now she's coming back. She's doing at least 40 meters at a steady rate, plus whatever distance she covered when she was accelerating. Now think to yourself, where is that going to bring her to? Will it bring her back to the school? Will it bring her beyond the school? Will it not bring her back to the school? If I had to make a quick guess with no calculation, I would say she gets at least to the school and probably beyond. Of course, the actual numbers will tell me when I actually do a calculation, but I'm just trying to get a mental picture of what's going on so that when I get to a solution, I have some framework in which to judge whether I've been successful or not. If you don't think in this way, then you're going to have that lonely feeling where every question you do is really just a shot in the dark. Try to think physics by thinking the way I've been thinking through this problem so far. Okay, now, of course, most of you probably realize that we can figure out how far she traveled in here. We know there's acceleration, that's A. We know that she was stopped in the beginning, that was a V1. We know that she got up to a velocity of 4 meters per second, that's a V2. And we want to know how far did she go in this part so that we can add that to the 40 meters she went in this part. Any ideas here, folks? Is there some way with a V1 of 0, a V2 of 4, an acceleration of a half, you can find delta D? I'll give you a hint, there is. They're called kinematic equations, and you learned them in grade 11. So figure out this number, how far she went here, tack that on to the 40, and now you've got a pretty good idea of what the picture looks like, and you can do the first thing. Make a rough sketch of a velocity time graph. So I don't want to give away too much more here, except I'll get you started on the velocity time graph. Remember, a velocity time graph might look something like this. It's got your velocity in meters per second, and you have to pick a direction. Since she went south most of the time, or at least in the beginning, I'm going to pick south as my positive direction. This is the time in seconds. And they ask you to label the important numbers on each axis. What do we mean by important numbers? Well, she started from rest. So 0 is an important number. She ran at a constant 3 meters per second. That sounds like an important number because that's the value of her velocity for a certain time. So let's put that in there. It said at some point that she ended up going north until she reached 4 meters per second and then continued at 4 meters per second. So that's north, that's negative south, that's somewhere down here. Here are some important numbers. Now, when you're doing this, think of the shape of the graph that you're going to create. Think of the slope, up or down. Think of where you might cross the axis, where might there be an intercept. And that's all I'm going to say at this point. I think I've given you enough to get started, and with a bit of discussion within your group, you ought to be able to take this a little bit further. Once again, remember to think about what does slope and area have to do with a velocity time graph? How are you going to calculate the displacement? Picture is going to help, graph is going to help, total distance, and so on. And then finally, I'm going to leave you with a challenge. From the velocity graph and your diagram, see if you can make a position graph that corresponds. Same thing, label the important numbers, and of course, E is just a little bit of a joke. That's me trying to be funny. Now you know why I didn't become a comedian. It's because my jokes are just awful. All right. Next question. Question 3. This one has a car accelerating from 10 meters per second west until at a certain acceleration rate for a certain amount of time. All right. How do you solve kinematics? In this case, we're dealing with one-dimensional motion. We're given a constant acceleration. Here you can use your kinematic equations for uniform acceleration. I do have a YouTube video on this that you can check out on my channel. The actual title escapes me, but it's probably very close to this. Ask me in school or send me an email and I'll send you the link if you can't find it. But for these ones, pretty straightforward. We're starting with a V1. We go for a certain amount of time. We have a certain acceleration. You're asked for something like the final velocity. That's a V2. So go pick a kinematic equation that relates these 4 variables. Look in your textbook or on the equation sheet that I'm going to send all of you by email if I haven't already done so. I'm sure you'll be able to pick a kinematic equation. Proceed in a similar way for part B and part C. This one's pretty straightforward. I don't anticipate too many problems here. If you want to take a look at the solutions, by all means look in the solution binder. Okay? Moving along. A ball is thrown upward at 20 meters per second from ground level. Use kinematic equations to answer the following. What is the maximum height? This one a little bit trickier than the previous question where you used kinematic equations because now you're dealing with, there doesn't seem to be much information given here. Let me explain. A ball is thrown up at 20 meters per second. That's an initial velocity. What is the ball's maximum height? Like, okay, well that looks like a displacement to me, but given V1 and delta D, I can't tell you much of anything. Unless you move at a constant velocity, I can't tell you how far you go unless you even tell me how long you've been moving for. How do we solve this? This question incorporates what's called implied or hinted at information. What information is hinted at? Well, you're throwing a ball upward. That means that gravity is influencing its motion. In fact, the acceleration rate will be due to gravity. Do you remember what the acceleration rate is due to gravity? How many meters per second squared is it in the downward direction? Well, there's a hint. That gives you the acceleration. You actually know it. It's implied by the nature of the problem. But there's also another piece of implied information, and that is the implied information in the words maximum height. When you throw something in the air, and it goes up, 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 just before it comes back down, it reaches what we call maximum height. What happens at maximum height? I'm going to leave you with that thought. You have to figure out what happens at maximum height. Maybe you should be sitting at your desk right now and throwing something in the air and catching it to see what exactly happens at maximum height. Once you have that, I think you'll see there's enough information to solve this using kinematic equations, the same way that the previous question pretty much gave you everything you needed and you used kinematic equations. All right, so sorry to be so brief on these last two questions, but I do want to leave you with some sort of challenge, and those are my hints for the Grade 12 Diagnostic Review of Grade 11 Motion Unit handout. Hopefully you'll make it through that without too much trouble. Make use of all your resources, and remember, always draw diagrams and write down what it is you are looking for. All right, thanks for watching. If you have any more questions, you know how to get those answered. Take care.